Today, I want to explore whether AI can help with a very specific problem in industrial data analysis, and that is the problem of schema mapping. Now, in the modern data world, think cloud warehouses, DBT, and so on, this is a well understood problem with many standardized solutions. But in the world of industrial data processing, it's still a giant headache. And instead of working with structured tabular data in a data warehouse, you're dealing with the thousands of arcane signal names coming off physical machines, all dumped into a data historian or a time series database, and there's just no DBT-like solution for that. So what do people do? Engineers sit down with spreadsheets or XML or JSON and map raw signal tags to their own internal domain concepts like program status, time in cycle, parts produced, and so on and so on. It's quite tedious, brittle, and expensive. So I started wondering, could we use AI to take some of the pain out of this? What if we could get the manuals for these machines, the official signal documentation, for example, to help us map tags to higher level concepts? Now, first of all, full disclosure, I come from the IT world, not the OT world. So I'm approaching this with a very fresh, naive set of eyes. But yeah, I'm still curious if AI can help. And for this experiment, I grabbed the reference documentation for a Siemens numeric CNC machine, a 1,200-page beast that lists all the variables and signals that the machine emits. And previously, that kind of document would have been too big for AI to process all at once. But now with models like Gemini 2.5 Pro, we can fit the whole thing into the AI's context window, or temporary memory, if you like. I mean, just barely. It fills up about 80% of the context window, but yeah, it works. So the first thing I tried was feeding Gemini a prompt describing some very high-level typical business goals. For example, suppose you have a CNC center and you want to measure specific metrics. So I asked it to tell me what signals I needed to track to count the number of parts produced, the overall equipment effectiveness, tracking operational data that could be useful for ERP or scheduling systems. And I did this, by the way, because some customers have told me that they don't know exactly what signals are going to be useful in advance. So they kind of need to dig out the signals through trial and error. So I was just curious if the AI could do some kind of requirements analysis in advance. So I basically asked it, what signals would you track from the xenomeric machine? And I also gave it a specific format to follow. I wanted a table with signal names, descriptions, and what have you. And crucially, a column explaining the business value of each signal, like why is it worth tracking? I also added a minimum length constraint for the number of signals because AI models can be quite stingy when it comes to long outputs. So I said, give me at least 50 suggested signals. And so Gemini returned a table with 82 signals. Now, I'm not a Siemens expert, and I couldn't judge the accuracy myself, but I did have something to compare against. Now, I actually have a manually mapped config file from a real customer who'd gone through the painstaking process of mapping raw OPC UA signals to canonical signal names, about 112 in total. So I compared the two. And so of the 82 signals that Gemini suggested, 49 matched what the human had also chosen to map manually. So that's 49 out of 112 hand-mapped signals. So if we take that example, Gemini didn't do that well, but at least when starting from vague high-level goals. Now, what if we gave it something more specific? So instead of these high-level business outcomes or business goals, we gave it a shopping list of canonical signal names. So basically machine-agnostic semantic labels that the customer used in their configuration with the mapping stripped out. So just the shopping list of labels. And so the idea is simple. Let's see if Gemini can find the entries in the Siemens manual that correspond to these canonical concepts, even if the names don't match exactly. And this time, the results were much better. So I loaded its output into a spreadsheet and compared it side by side with the human-created config file. And for many of these semantic names or semantic labels, things like active tool radius, parts counter, program status, Gemini correctly found signal descriptions in the manual that matched the intended meaning. Interestingly enough, there were also cases where Gemini found entries in the Siemens manual that the customer hadn't mapped. And some of those might be noise, but others could be genuinely useful. I don't really know. especially for other machines and use cases, perhaps. And there were also a few fuzzy matches that it wasn't confident about, which it flagged. And there were also canonical signal names from the customer config that simply didn't exist in the Siemens manual. So, of course, it couldn't find those. For example, signals related to table rotation, which the xenomeric machine might not support. So in those cases, Gemini correctly didn't return anything. So the takeaway here is that if you start with vague goals, maybe AI will struggle or you won't get much out of it. But if you give it a list of concepts that you're interested in, even just human-readable names, it can do a pretty good job of connecting those to signal definitions in the manual. And of course, all of this assumes that you know precisely what you want to track. But what if you're still not sure? So I spoke to one customer who had to literally activate different functions on the machine, turning them on and off, and then dig through the time series data to figure out what changed. And that's how they figured out which tags corresponded to which physical actions. And it worked, but it was slow and very labor intensive. So what if you just ingest all the raw data from the machine, don't try to map it yet, and you just pull in everything, and then you cross-reference those raw tags with the descriptions in the manual. And then you feed some actual data samples to the AI. And so now the AI isn't just guessing from the names, it's also looking at the shape of the data and how it behaves over time. So does it spike? Is it binary? Is it cyclical? All of that can help the AI to infer what kind of signal it is and what high-level concept it might correspond to. So the customer I mentioned earlier didn't use AI, they just use Quix Cloud to ingest and visualize the live data. But that setup gave me an opportunity to test the idea. So I created a simulated version of their data, not the real data, just a mock-up, and pushed it through Quix. And so that data was streamed into a Kafka topic, and I used a basic visualization layer to look at the raw signals. And even that simple view helps to reveal patterns that can guide those mapping decisions. And so if you were to combine that with an AI, maybe clustering signals based on their statistical features or temporal behavior, you could probably build a much smarter mapping system. And I'm not the only one who's thinking along these lines, by the way. The OPC UA Foundation itself actually has an AI working group tackling problems like this. And there's also plenty of academic research, including a paper out of China that I found where researchers took user manuals and signal descriptions to automate this tag to concept mapping. And this is really the kind of thing that Quix excels in. So ingesting, transforming, and analyzing real-time data streams and enhancing that with some kind of AI model. Now, of course, there's a lot more that we could explore, like AI agents, vector embeddings, similarity search, time series clustering, all that good stuff. But I hope at least this short video was a useful intro into what's possible already using no custom tools. So if you're interested in seeing more experiments like this, or maybe even us building out a full mapping assistant, let me know and I'll put together another video. Anyway, that's it for now. As always, thanks for watching and see you soon.